All right, good afternoon. Let's get started. All right, so today we do multiple things. First, let's wrap up chapter 8, and then we'll talk about the problem from exam 2. And then do a quick review and go over examples. Practice, right? So we'll go over that. All right, so last time we mainly talked about pressure vessel. And this actually we use it a lot, because in our life you see around us there are a lot of pipes, can be gas pipe, oil pipe, any kind of pipe, always under pressure. And safety is a concern, so you basically need to find out, what's the stress in the pipe to be able to design, make sure it's safe. Okay, so we end up two simple equations for thin wall tube. Okay, so remember the wall thickness is really thin, and we talk about that situation. Okay, for tube, you're going to have circumferential stress, and we call it. Okay, anyone remember the term we gave it? Hoop stress. Okay, so it's a hoop stress, or sometimes they call it Laplace stress. It's the same thing. All right, and that's given here, sigma 1. That's a circumferential direction. So you're going to have the stress determined by pressure, radius, and the thickness. So that's the way you can estimate the average stress there. Okay, again, that's an average stress in the wall, across the wall thickness. If you learn more advanced material, the wall, if you look at the cylinder, okay, so the actual wall stress will be something higher here and low here. So you have this kind of distribution. But for us, we talk about thin walls. So we ignore the thickness, so basically average out. That gives you the average. Okay. In other words, if you have a little bit not so thin wall, maybe a thick wall, like an artery, you can still use this to do estimation. What's the average stress? And we're using it a lot, because sometimes for really thick wall, you can still use it to estimate. Just remember, it's estimation. The walls, the thinner the wall, the accurate this equation will be. So for the veins, because it's so thin, you can use this one perfectly estimate the stress. But for arteries, remember just estimation. Okay, so we end up with these two equations. Then at the end, class asks you to look at if I have a limit length of the cylinder, like a Coke can. Okay, what's the stress in a Coke can? Circumferentially, you're going to have this much stress. Right? But the longitudinally, you're going to have a sigma 2. And this is the same equation as you have a sphere. And that's how you calculate the stress in a sphere. And so, because of those two equations, right, you can quickly calculate the stress in the circumferential direction and the longitudinal direction. Okay, and always, as you can see here, the longitudinal one is half of the circumferential one. Okay, so then I ask you to see if you can draw the Mohr circle, determining the principal stresses and the shear stress. Okay, anyone try? No? You should try homework, right? Okay, all right, let's do it together then. Okay, so if you look at a piece from that Coke can here, okay, here is what you have. In one direction, you're going to have the sigma. Right? Another sigma 1. In another direction, you're going to have sigma 2. So here we know the sigma 1 will be 2 times the sigma 2. Right? So let's say we can calculate. You have a pressure, you have the radius, you have the thickness. We can calculate. Let's say I find out the sigma 2 equal to, give a value. 5. Okay. I like small number, easy to calculate. Right? Okay, if this is 5, what's the sigma 1 then? Sigma 1 will equal to 10. Okay, so then if you look at the piece of that Coke can on the surface, okay, this square going to under 10 in this direction, 5 in this direction. So longitudinal 5, circumferential 10. So that's the element we draw here. Now, what's the Mohr circle? Can you draw the Mohr circle for this? Let me see if I have it here. No, I don't have it here. That's just the equation. Okay. What's a Mohr circle? Okay. So here is a sigma axis. Here is a tau axis, right? Okay. Where is a circle? Where is point A? Where is point B? Point A is a sigma x, then tau xy, right? So what's the value then? Where's A? So it'll be sigma x. Which one you call x? Actual direction, right? The sigma 2 direction. Okay, so you have 5. What's the tau on this surface? On the side? It's 0. So 5, 0. Okay, so this point is here. 5, 0. Where is point B then? 10, 0. So it's here. 5, 10. Should maybe make it a little bit bigger. So 5 is here, and then 10 will be here. So this is point A, this will be point B. Now, what's a circle? You just draw through these 2 points, right? That's a circle. Now, with this circle, what's sigma 1? What's sigma 2? I mean the first principal stress, second principal stress. 10 to 5. So the sigma 1 here is actually the first principal stress. And the sigma 2 here is the second principal stress. Okay, now what's the maximum shear stress? Radius. Okay. So radius will be this radius, right? This is the radius. This is radius. This is also radius. What's the value? 2.5. So maximum shear stress is 2.5. Right? Okay, this is the Mohr circle version. Now, if you say, I want to find out the principal stress, find out the shear stress using the equations, then here is the equation version. Okay, so it's basically here. This is the equation. Okay. Now, is this the correct equation? Yes, that's the equation we had previously. Right? If you don't, you're still in doubt, go back to the, we will show actually the formula sheet where is the equation. Actually, I can show you right now here. And switch to okay, so here's the equation. You make it a little bit bigger. All right. Okay, where's the shear stress equation? Actually, I missed that one. So I need to add it to it. But actually, it's there. Which one is the shear stress equation? What's the shear stress? It's the R, right? So R is there. I just didn't call it. So the maximum shear stress is equal to R, right? Okay, so I'll add that to this formula sheet. And then, okay, now R, what do you see here? If you look at the R, this calculation here. Now, how can this one equal to the equation we just said? We put it like a tau maximum equals to half sigma 1 minus sigma 2, right? That's how I calculate a second ago. Now, this two the same equation. Yes and no. Looks like different, but it's basically the same. Because what's my sigma x? It's a sigma 1. What's my sigma y? It's the sigma 2. Okay, what's the tau xy? It's a 0. That's why it's the same. Right? Okay, so tau maximum equal to R, and that will be added to the formula sheet. All right. Okay, let's go back to what do we have here. All right, so we have the tau maximum. Okay, so the next example I want to go over quickly is this actually a practical problem. Okay, So how do you build the cylinders? There are many ways you can build it, right? You can put the pieces together, or one whole piece, make it one whole piece, right? That's another. Okay, here what they build the cylinder is by rolling a band, rolling a sheet, and you just roll it, and then you build this cylinder. Anyone try this way? Build the cylinder before, like use paper, right? If you have a sheet of paper, let's say this is a sheet of paper, right? I'll use this one. Okay, so this is a sheet of paper. Okay, how can you build a cylinder with this piece of paper? You rotate, and that's a cylinder, right? So once you rotate, you glue this together, right? You weld them together. So here, then you basically have a cylinder, and that's how they build this one. Okay, so when built this way, then the issue will be, okay, what's the theta? That's a line, right? That line you have a direction, theta direction. So what's the stress on that surface? Because if this one fail, most likely you will fail along that line. You're not welded strong enough. The glue, that would be one concern. So you want to know what's the stress along that line, right? Okay, say we know the pressure inside, we know the diameter, we know the length, everything. Okay, how can we find the stress along that line? How to find it? You can use the equation, right? Basically, that's a rotation question, right? If you look at this piece here, you basically have, this is the sigma x, this is the x direction, this is like the y direction. So you have sigma 1, sigma 2. That's basically the stress you already have. Now you want to find out the stress along this line. How do you find it? Use the equation for stress rotation, right? Coordinate rotation. Or draw Mohr circle. Right? So you can either use the equation I just showed, or just use the Mohr circle to find it. Right? And here is actually this cartoon showing what's the stress along that direction. But how to calculate, you can use the equation or use Mohr circle, right? Because from here, let's say this one here, 36, 72, right? Because we know sigma 2 will be half of the sigma 1. Okay, can we draw a Mohr circle for this one? Oh, it should go this way, right? How it go this way? Okay, can we draw a Mohr circle for the stress condition here? Yes, so you're going to have sigma 2, that's the 36, right? That's a 0.8, and then 72. So that's the sigma. Okay, so then you draw the Mohr circle. Okay, now if I know this direction, okay, see what's the gap here? 35 degrees. Now if I want to find out in this direction, 35 degrees from this axis, what's the angle? I mean, what's the stress? How can I use the Mohr circle to find it? Where that point will be at 35 degrees? 70, right? 2 theta here. So on this surface, I need looking for, okay, from here, you go up 70 degrees. Okay, this is the point that follow that 35 degree direction. So the stress here, basically the coordinate here. This point, you have a sigma x and a tau xy. And that is actually, will be the sigma theta and the tau theta. That's how you find the stress. So you can use a Mohr circle to find the stress at any direction. Just remember, this part must be twice the theta as shown here. So you need a 70 degree. Okay, any questions? All right, if not, I think we'll wrap up this chapter 8. All right, so next I want to go over quickly what we already covered so far. All right. Okay, so I'll use a formula sheet. Let me pull up that sheet here. Okay, let's see. I can make this a little bit bigger. Which one should I click on? Tools. I need to cancel this part. Okay, all right, thank you. All right, so here is basically a quick summary what we learned last 3 chapters, and actually what will be covered in this coming up exam 3. Okay, so we basically talk about deflection of a beam. Okay, so it's more, I would say, more skill kind of knowledge than just equations. Okay, it's basically how to find the deflection, and the equation is actually, if you want to put it in the formula, it's very simple. And there's only three equations, as you see here. So we call it moment equation, or shear force equation, or load equation, right? So that's the 3 equations. And that equation about deflection V. So for any given problem, you can start with these equations, find the deflection by integrate, right? So depending on the equation, you need to integrate twice, 3 times, because sometimes, for example, for this one, let me see, how can I guess you need to push 2 again. Well, I'll maybe not try it right here then. Okay, so for this equation, for example, you just integrate two times, and then use a boundary condition to determine the integral constant, C1, C2, right? If you use the very last equation, the Q, load equation, then you have to integrate 4 times. Use a boundary condition, determine the 4 integral constants. Okay, so, and that's how you find the deflection, right? So that's a tedious process. You have to do the integrate once, twice, 3, 4 times, right? And then find it. Okay. An alternative, or much easier, much better way is using superposition. Okay. The reason superposition is better because when you have most of the case, you're going to have multiple load, and you can divide it up, find the solution of each one. And for each one, actually, you don't have even to find it. You just look at the table, find the solution. Okay. So here is a key skill. You need to be able to look at the table, find the solution you're looking for. Yes? Yes, if we need a deflection, we'll give you the table. So the table will be provided. Again, you don't need to bring, or just make Xerox copy, give that away. All right? Okay. But make sure, I gave you a table. You know where to looking for what you need, right? And one thing is, you use which equation listed in the table. Okay. So they may give you, for example, give you the whole solution, Vx, V as a function of x. They also give you the maximum point, or they may also give you the rotation angle at certain point. So you need to look at the question, what they're asking for, and then select the right one. And oftentimes, if you use that specific solution, for example, they give you the maximum. So directly use the maximum instead of using the Vx equation will save you time. Because you don't need to plug in the x and then calculate that value. They already calculate for you. Right. So superposition will be a key here. All right. Because from homework you can tell, if you do the integrate method, you may, let's say, take half an hour to solve a problem. But if you use the superposition, maybe just 5 minutes. So that's the difference. All right. So make sure, whenever possible, use the superposition. All right. So in terms of equation, actually not much I can put there, the formula sheet. All right. So it's just that's 3 equations. All right. I stretched this a little bit. I put this principal superposition there, but that's actually not the formula equation at all. All right. Okay. So it's more skill using that superposition to solve the problem. Okay, the next chapter is indeterminate problems, indeterminate beams, and that basically a repeating of this determinant problem, except you're going to have multiple, more than enough restriction. So the key here is you need to identify a load that is redundant. So you remove it and then replace it with an unknown load. So you label it called either RA or RB, or you can call FA, FB, or maybe there also can be a moment. You can call MX or MR, what you call it, right? So you replace that redundant restriction as an unknown load. And then you can solve that problem as a determinant problem, because that's what we call reduced. Let me see, I have it here. Okay, so we call it reduced structure. And you need to know what's a reduced structure. Indeterminate, you select the load, redundant load, change it to force, then this structure becomes determinate. Okay. So that determinant, then you can solve it, either use the equation method, all the equations, 3 equations we just did, or use superposition. Now again, whenever possible, use superposition. It's much easier. It'll save you lots of time. Okay. And the compatibility, right? Remember we always say fat dot count. Okay, so the F part, free body diagram, that's the same, right? Equation of equilibrium, that's remain the same, right? The deformation equation, actually, you can find from the table. And the key will be compatibility. So compatibility here is basically a boundary condition, right? So we just say, actually, sounds very abstract, very theoretical, right? But actually, that's what we're doing. So you find the compatibility, that's a boundary condition. Okay, because it's so abstract, so we'll go over maybe a couple more examples as well. All right. So this are more scale kind of thing. You can solve, use superposition, find the deflection of multiple load. Okay. And another one is use a superposition, find solution for indeterminate problem. Okay. So these 2 chapters are very scale-based questions, problems. So therefore, you have to be able to practice and then know how to do it quickly. That's it. For example, I can give you a table. Someone find the solution from the table in a second. Someone looks around, looks like this, look at that. You can take 5 minutes, just look at the table, find your solution. So therefore, you need to get familiar with the table. All right. Okay, then it's chapter 7. Okay, here involving both scale and equations or the formulas. Okay, so the goal for us is whenever I give you a stress at one point, oftentimes it's a plane stress, right? So we'll need to know in which direction you have the principal stress, the first principal, second principal, and which direction you have the maximum shear stress. So you need to be able to calculate all these values. What's the sigma 1, what's sigma 2, what's the maximum shear, and which angle, which direction it takes the maximum. Okay, so here are all the equations you need to calculate all these values. That's, you just follow the equation, so that's one. But in addition to this, we kind of learn a scale that's called Mohr Circle. So you're able to draw the Mohr Circle. And the key is find out the point A and point B and point C. Point C, of course, the center of the circle. C is very easy to find, right? So as long as you can label A and B out correctly, then the circle part is easy. And it's a little bit scaled one that will be you need to get familiar with is once you have the Mohr circle, how can you find the sigma 1, sigma 2, and the maximum shear and the principal direction from the Mohr circle? And what we just did, right, for the cylinder, right, we just practiced actually. So that's the requirement. Right? Either use the equation, calculate, also draw the Mohr circle. Okay. So if I have a question, ask you to do all this, then the grade will distribute between Mohr circle and the values. Right? Sometimes people get the values correct because they just follow this equation, and oftentimes draw the Mohr circle wrong, something wrong there. So you need to practice both the scale, how to draw a Mohr circle, and find out all these values. Right. Okay, so the very last part of that chapter 7 is about the Hooke's law there. Okay, and then we talk about this Hooke stress in cylinders, and this part actually my intention is not to put this part in this exam 3. Okay, so we'll mainly focus on chapter 7, chapter 9, and chapter 10. So chapter 8, this content, I think I'll put it maybe in the final exam, but not here. because we already have a lot there. You have only 1 hour. I cannot give you 5 problems to solve. 50 minutes. Yeah, I'll try again. I can extend to 1 hour. Okay. But again, let me remind everyone, when you come to the room, make sure you sit apart. You know, last time we sitting here, everyone next to each other. So I have to move people. Some of you lost maybe a couple of minutes by moving to a different room there. Maybe this time we'll do until everyone sit, and then we'll start. So this way everyone will be fair, get the same amount of time. So just make sure we just need your next seat will be empty, so away from another person. Okay, so this is a formula sheet. I will modify this part, add the tau equals R to this equation. Yes. All right, any questions about this part? That's chapter 9, 10, and 7. It's the deflection of the beam, indeterminate beam, and the Mohr stress analysis, Mohr circle. Okay, any other questions? Questions? Okay, if not, let's go over a couple examples. That basically we need at least one example from Mohr circle, one example for indeterminate beam, one example for determinate beam. If we cannot finish today, we'll continue talk about the example Friday as well. Okay, so we'll start with the simple one, determinate beam. All right. Actually, I will start with one question. You tell me it's determinate or indeterminate. All right. So okay, so my first question is, you have this beam. What do you call it? Cantilever beam. All right. Okay, so this beam, we have a load Q. Okay, you can give a value or just use Q. That will be fine, right? And then we're going to have a concentrated force, P. Okay, and then we're going to have another one is a bending moment here. So all this value are known. Okay. And my question is, okay, how much deflection you're going to get at this point? Let's say this will be point A, this will be point B. I want to find out that when I apply all the 3 loads onto this beam, how much this beam going to move, right? And I care most about the maximum value, and so the T. So I want just ask this one. So what's the value of the B? Or you can say call delta B, right? You can use either way. It's mean the same thing. Okay. How can we find this deflection? Superposition. Okay. Of course, you can also use the equations, right? You can use EI, for example, EI V 2 prime equals M. And integrate twice, use a boundary condition, and then solve it. Right? That's one way. You can do that, but that will take quite a while. I won't be able to finish if we do that. Okay. But the easy way is always superposition. Now, superposition. How can we use the superposition to find the solution? Okay. I ask you to bring the book. Anyone actually have the book here? Okay, how can we find the solution? All right, let me switch to the projector. All right, so if you look at the table, okay, so there are many pages. Okay, if it's this very first page, it shows this cantilever beam. So that's the part you need looking for. Don't looking for the simple beam for your solution, right? So first, which kind of beam you're looking for solution? So this is a cantilever. All right, now this one page will be page 2, and then page 3. So there are actually 3 pages of solutions they give you. Okay, now which one you need? Which one? The first one, number 1, right? Because that's a distributed load. Okay, so that's one part in the, okay. So if you look at this table, okay, so for distributed load, all right, they give you lots of information here. They give you, let me make it a little bit bigger. They give you the solution for the deflection V. Also give you the V prime, the angle, as well as the deflection at point B and the angle at point B. Okay. So which one would you use for this question? Delta B. Because I care about the point B, right? The question was about point B, so I can just answer the question for point B. I don't have the answer for all the other points. That's what not asked. Okay, so we'll need this one. So I'll copy this one down. So that will be 1/8, right? Okay, so I'll just write down now, switch over. Equals 1/8 of EI QL4. All right. Okay, let me switch quickly over so you can see what. All right, so I copied down this equation here, right? Because I know this delta B will be equal to what? Equal to the V of B. Or you maybe should write delta better. The delta B from load Q, and then the delta B from load P, and then the load delta B from load MO. That's what I need, right? Superposition. Okay, so we find the first one from the Q. Now let's go back to the table, see if we can find the other one. What's the next one we need? It's not here. So check next page. Which one? Number 5? Okay, or number 4? Number 5 is somewhere in the middle, right? Okay, so for number 5, okay, there are lots of equations here. Which one should he use then? Which one? There are so many equations here. Which one are you looking for? You want to find out delta B, right? If you tell me delta B, then I don't care what are other things. But if you don't tell me delta B, I have to know other things to be able to calculate delta B. In this case, they give you delta B. Okay, so delta B is here, right? So it will be PA squared. Okay, 6EI and 3L minus 8. Okay, I'll just copy down this. So there will be delta B from the P will be 16 PA squared. PA squared 6EI and then 3L minus 8. All right, so that's the one. Okay, what's the next one? Number 6. Okay, so number 6, they give you, what they give you? Which one? They give you 4 equations right there. 4 solutions. Delta B again, right? We care about delta B. So delta B, I'll just copy this one here so we don't have to switch back again. So it'll be MO and then L squared and then 2EI. Okay, that's the solution for this one. Okay, we found all 3, right? So now let's switch back to switch back to what I copied here. So I wrote down this solution. This one is for, you have a load here, right? P, and then this part is A. Okay, now that's a solution you can find from the table. That's the closest one you can get. Now what's next? It will be depend on your judgment or your input, right? Okay, so the very first one, do we need to modify this in any way? No, we can use it direct right away. Okay, now the second one. How can we use the second one? What's the A? So your A will be half L, right? Or if you know the value, let's say L equals to, give to, say, 8 meter long, right? Then your A will be 4 meter long. So this will be 8 meter long, right? We know this load happened at the middle. So whatever the A value they give you, you just use it. So then you plug the A or the A in there, you get the solution. Okay, now the very last one. This one, do we need to do any modification? Okay, what's the modification we need? Should be negative. Very easy, right? Because the solution they give you, M is pointing this way, downward. And the situation you have is going upward. So therefore, you need to just add a negative sign there. And that's it. Or in other words, your delta B from the MO is going to be upward. Right? All the other load make the point B moving down. But this MO makes the point moving up. That's why when you combine them, they will cancel a little bit off. All right. Now can we find the solution? Yes. Okay. Then we're done. How many minutes does that take? Can you finish it in 10 minutes? Right? From start to end, no more than 10 minutes. But if you use the other way, I say you can take at least 30 minutes. All right. Yes. Yes. It's actually say in this table, say, I'll give you the table. Right. All right. Any questions about this example? Yeah.
Don't B and delta have opposite senses? So whereas in deflection is considered to be positive down, but delta is negative down.
Yes. Okay. Here's a question. If you look at the table, okay, they give you Vx. They also give you delta. But if you look at the Vx, you plug the x value, x equals L. What you get will be a negative value. Because the V, the sign is pointing upward. So the delta is actual absolute value. That they say, oh, this point is going to move down, delta. So that's the distance. So yes, if you use the V to calculate, V equation to calculate, it will show up as a negative value. So if you use a delta B equation to calculate, it will show up as a positive value. So that's it. All right. So here, that's the one thing you need to just a little bit careful is the sign. Okay. When you have this load, at this point moving up or moving down. Or if the load flip direction, this point moving up or down. All right.
When you use the V for shear force, you use V.
Which, oh, this V, capital V, we remember we talked about VM diagram. So the capital V, we represent the shear force. And the capital M, we represent the bending moment. Right? And also again, okay, this will be the shear stress, and this will be the normal stress. Okay, I saw a few people get confused last exam about which one is the shear force, which one is the shear stress. They are related, but they're totally different things. One is force, one is stress. So that's more a concept issue. You need to understand which the concept. All right. Okay, any other questions? Okay, if not, let's go over another example. Okay, here is a beam. Okay, this is a pin support, and there is a load here, and then there is a cable. Okay, so I know the load, I know the beam. Let's say this is a half length. Let's make it easy. Let's say in the middle, although it looks like not in the middle, right? But anyway, those two lengths are known, and this cable here we know everything, EA and the length. Right, so this will be E, maybe prime, different one. Okay, A prime. This can be different material compared to the beam. Okay, now I apply load P, and I want to find out how much this point B move. And maybe also find out how much this point C move. All right. Actually, quick back up here. I can ask you another question. How about this point C? How much the point C move? Can you find it up? How much point C move? How do you find it out? You use a V equation. You can just add them together. In this case, because this table doesn't give you, the middle point, exactly what's the delta at the middle point. So you have to use the Vx equation, right? So you just put in the Vx equation, but make x equals half L. And that give you all the deflection at the middle point. All right. Okay, so how can we find the deflection or the displacement at point B? And it looks like we're not able to cover more examples. So we'll end with this example, and then we'll continue next time, Friday. Right. Okay, so how can we find the displacement of point B? Is this a determinate structure or indeterminate structure? Determinate or indeterminate? Determinate. I heard a different voice. Okay, I'm not sure, right? There are point A and point B. Okay, so let's try it. Okay, equation of equilibrium, right? That's how you judge whether you get it determinate or indeterminate. Okay, what's the equation of equilibrium? Well, first you need the free body diagram. So you're going to have RA here, right? What else? RB. There are RB there. Yes, you're going to have RC. So for the beam, there is a RC here. Anything else? That's it, right? Two reaction applying on the beam, or the two restriction applying on the beam. Okay, two unknowns. Is that determinant or indeterminate? I still heard a different voice. It's determinant, right? Okay. Remember this problem? Is this one determinant or indeterminate? It's indeterminate. Because there will be RA and MR and this load RC. Three unknowns. So 1 degree of indeterminacy, right? But the top one is determinate. Okay. So at this stage, you make sure you draw the free body diagram and judge it's determinate or indeterminate. Because that will help you decide, which way to go. It can simplify the problems. All right. Okay. So for the top one, how can we find the solution for this point B? It's determinate. So therefore, you don't need all this thing for indeterminate stuff. It's much easier problem, right? And next time we can talk about this one, the bottom, how to solve that one. Well, you can see the difference there. Right. Okay, let's talk about the first one. Okay, what we can do to find out point B? Displacement. Movement, I already wrote, right? Sigma m, any point, A equals 0, right? Or sigma Fy equals 0. So basically from here, I can find out RA and RC. So RA, RC will be found out from equation of equilibrium. So all this load will be known, right? Okay, you're not sure? Let's just write it. I think that won't take too long. Sigma Fy equals 0. So let's give this one, let's say 10. All right, so you have RA plus RC minus P equals 0. Right? Okay, second equation. How about sigma m to point C equals 0. Can I write this equation of equilibrium? Yes, right? Because to any point it's supposed to be equal 0. Otherwise it won't be equilibrium. Okay, why I write RC? Because I feel this is easier. Why is it easier? You can see here. Okay, to point C, what's the moment? You have RA generated moment times half L. And that is clockwise. So it's negative. And then you're going to have P times half L in the clockwise direction as well. Right? So these two add together should be 0. Is that correct? Okay, now what's RA? Equal to P, but the other direction. It's actually equal negative P, right? So RA will equal to negative P, and that means negative 10. And that means RA is actually this way, 10. Okay, now what's RC? What's RC value? Negative P? See here, you already have this equation. Put the RA and into this equation. What's RC? 20. So RC will equal to positive 20. Because it's, right? It's the same. You have 10 here, you're pulling, you must hold in 20. So, intuitive, right? Okay, so we know all the reaction forces now. Okay, now how can we find the delta B? Do you need to find outcome? It's determinant. It's much easier than that. Okay, how can we find the point B then? Okay, first you need to can give a sense how this thing moves. Okay, when you have this beam there, right? Now imagine you're pulling here. This point is going to move down, right? Why this point moving down? Why? What causes it moving down? The force. Okay, why the force causes it moving down? Because you have a beam here. The beam is going to bend. So that bending will make it move down. What else can make it move? You have a cable here. When you pull, okay, so you pull in 10 here, and the cable is under 20. So the cable is going to elongate. Imagine you have like a spring, right? The spring, this point C is going to move it down, right? So if point C move down, point B, of course, will go move down. So you have two deformation here, or displacement here. One is this point C moving, let's say, let me just draw it here. Okay, this point C going to move down. So point C move to here. Then this point going to move twice as much. Okay. So can you find how much this point C going to move down because you are pulling? Yes, because you know RC, right? We already know the delta of the bar equals to the RC times H over EA, E prime, A prime. So you can find how much C point move. Okay, then the point B has to move twice of that distance. That's the first part. The second part, the beam going to deform, right? Okay, can we find out how much the beam is bending? Let's say if you stand on the beam, right? So if you have a beam here, right? You have a load pulling up, a load pulling down. Can you find how will this part move? How much deflection? I mean the point B. How much the point B going to move? Can we find out that? We just did, right? Previous example. So you can find this one. So this, let's call this one delta B from the bending, right? This one delta will be from the point C moving down. Now, what's the final? Add them together. Superposition. Right? That's how you get this. Okay, so let me write down here again. So the delta B from the point C, this point C movement, you will get basically twice of this. So basically 2R C H E A E prime A prime. And then this one, can we find this solution? We had it previous one, right? Because here you know this will be 20, this will be 10. So this one, so the delta B from the bending supposed to equal to the delta B because the 20, right? That's in the middle. So that's the RC. And the delta B from this load P, and that is 10. For each one, we can find it from the previous one. Okay, you can find all this too from the table, right? The easy way, again, use superposition from the table. So it's like first you divide this into two portions, and then the second portion you divide into two load and deformations. All right. Okay, try do it, follow up. If you have questions, bring. Okay. We'll continue talk about more examples and more circles, and hopefully we can find a few minutes talk about the exam 2 solution as well. Yes.
I'm going to take an independent study. Did you sign?
No, there's nothing I can sign.
Oh, okay.
It's all blank. You need to get the first everyone, the instructor.
Okay.
Yeah, then I'm gonna be the last one to sign.
Oh, you're the last one?
Yeah, I'm
Okay, I
not the
just
first
thought
one.
because I'm in your classwork.
No,
Okay.
you have to get it.
But it's, whenever I get this filled out, I can just go to your office?
Yeah.